Power vibrations video. And in this video, we're going to be looking at a general forcing problem. So ideally, as you would have seen, is we have vibrations that are caused by forces that are not harmonic, right? So in this particular case, we are going to look at how do we analyze problems of vibrations whereby the forcing function is not a harmonic force, right? But instead, it's only a periodic force. Okay, so as you can see, we in this particular question, we are given that the following differential equation that is used to define this vibratory motion, okay, as shown in figure 1. We are told that is shown in equation in figure 1. Sorry, that was supposed to be. So the equation 1 is describing the differential equation for the motion. And we're also told that we have a periodic function, right? Which is shown in figure 2. So now what we are tasked with is we need to find the displacement equation, right? Or in other words, the response that best describes this particular system. Okay, so first things first, one thing that is important to note is that the forcing function is neither a constant force nor is it a harmonic force. Remember, when we define a harmonic force, it's a force that is periodic in nature and sinusoidal also. So by sinusoidal, I mean it either contains a cos or a sine, right? That's what we basically mean when we say that something is sinusoidal, okay? So as can be seen in this particular picture, right? So our forcing function, okay? So this is denoting our forcing function, right? But what we can see for this forcing function, right? It is actually being described by 3,500 multiplied by this particular function yt. Okay, now let us look more in detail what is yt. As can be seen in the diagram, we can see that yt is actually a periodic function. So it's periodic, right? But is it sinusoidal? No, it's not, because it is periodic, but it doesn't have the normal sinusoidal or sinusoidal shape. Okay, so what we are going to then do in that case, right? We are then going to conduct a process of converting a periodic force into a harmonic force, because already based on the work that we have or from theory, right? We can see that we have general solutions that are attributed to harmonic excitations. Okay, so if we can take a periodic function to a harmonic function, then we can use the general displacement equations that we have already developed or that are already available for harmonic excitation. Okay, so let us look first at yt. So ideally what I want to do is I want to convert this or right-hand term into a force, into a function which I'll call ft. Okay, so I'm going to say, well, ft is going to be a function. It's going to be a periodic function, but that is defined. We know that between the period. So I'm only interested in what is happening between one period, because I know that this particular function is repeating. Okay, so what I do notice is that ft, right, between the 1 second, looking at this particular period, the 1 second period, right, what I do notice is that ft is going to be equal to basically a straight line, right? So I'm going to still multiply it by that 3,500 that is shown there. But I see that it's a straight line that is defined by, if you convert that 25 millimeters to meters, just to make sure that I work with the SI units, I see that that is going to be equal to 0.025. Okay, then I have t. Okay, But maybe let me expand it further. So this is going to be equal to 87.5 t. Okay, but what does this mean? This function is only valid, remember 0.05 t is only valid on this particular interval. Okay, so that's where 0.05 t is valid. So this therefore means that our function f of t, right, if I rewrite it as a piecewise defined function, I can therefore say that, well, this function is equal to this 87.5 t if and only if t lies between 0 and 1. Okay, so that's what we have. That's what we have for this particular question. So what we have done so far is we have nicely cleaned up our right hand term there. Okay, so now we're going to go through a process of now converting this periodic f of t into a harmonic excitation. Okay, so what do we know? Well, we know that any periodic function, right, can be converted by the Fourier series, right? And what does the Fourier series say? The Fourier series says that xt, so let me just rewrite it, xt is equal to a0 over 2 plus the summation of, here we have infinity, then we have n is equal to 1 for cos an cos n omega t plus bn sine n omega t. Okay, so what this Fourier series is telling us is that in order for us to convert a periodic function into a harmonic excitation, we have to find these particular terms. We have to find what is a0, we have to find what is an, we have to also find what is bn, right? So if we have these particular terms, an, bn, and a0, we are able to fully define the function as a harmonic excitation. As you can see, this equation, this one, which I'll call equation 1, is periodic and sinusoidal in nature because we have the cos and the sine in the term. Okay, so now what I'm going to do is I'm going to now look for a0, an, and bn. Because what I do know is if I find those, then I know that I would have now been able to fully convert f of t from being a periodic to a harmonic forcing function. Okay, so what does the theory say in terms of finding a0? Okay, well, a0, let me just use the same color. So let me just stick to the same color. So, well, a0, in order to find a0, a0 is defined as 1 over t integral of t0 and the function, in this case f of t, dt. Okay, what is t? Where t is the period. So t is the period. In this particular case, our period is 1 second, as can be seen there. Okay, so this therefore means that, well, this is going to be equal to 1 over 1 integral from 1, 0, and what is our f of t? Our f of t is given as 87.5 t. Okay, so if you evaluate this integral, what you are going to get as your answer is that, your answer is going to be 87.5 divided by 2. Okay, so this is going to be the value for a0. Okay, so a0, we have found a0. Now let's go on to find what is an. Okay, so an is an expression. The expression to find an is denoted by 2 over t integral of from 0 to t of that particular function, f of t, right? But now we have a cos n omega t, okay? Cos n omega t dt. Okay, so now for this particular one, what you are going to then realize is, in order for us to evaluate this integral, so if I further clean it up, what you're going to see, that is going to be equal to 2 over 1 integral from 0 to 1 of 87.5 t cos n omega t dt. Okay, so what you will see, right, is if you use integration by parts, right? So let me just write it. I'm not going to do the whole integration by parts. So integration by parts, okay? So if you use integration by parts, what you are going to get is that, I think you're going to get an expression that stipulates that, well, an is going to be equal to 2. Okay, so I'm just going to now give you the resultant of that integration by parts, bracket 1 over n omega squared cos n omega t plus 1 over n omega. Okay, let me just neaten it up, yeah, because it's quite close to each other. Okay, so plus 1 over n omega. Then here we're going to have t sine n omega t. Okay, close bracket, 1, 0, our limits. Okay, and what you will see if you evaluate this, you're going to get that an is going to be equal to 0. Okay, so we've found a0, we have found an. Now we have to find what is bn. Okay, so bn, there is also an expression to find bn, which stipulates that that is going to be 2 over t integral from 0 to t, right? From 0 to t of the given function f of t. But now in this case, it's going to be equal to multiplied by sine n omega t dt. Okay, so like I have done for the previous one, so this is going to be 2 over 1, the integral from 0 to 1 of our function, which is 87.5 t, okay, 87.5 t multiplied by sine n omega t dt. Okay, so likewise, if you use integration by parts, right? So integration by parts, which I won't show in greater detail, but at least I'll show you how I went about to find the expression that I have below. So if you use integration by parts, what you will then get is that the final expression for bn, so bn is going to be given as 2 multiplied, so let me just say multiplied by 87.5, then open bracket 1 over n squared omega squared sine n omega t, okay, plus 1 over n omega multiplied by t cos n omega t, okay, close bracket, 0, 1 is our limits. So if you evaluate this, what you will then get is that your value for bn is going to be equal to negative 175 over n pi. Okay, so this is bn. So we have bn as this value, and from the previous page we found an is equal to 0, and we also got to find out that A0 is equal to 87.5 divided by 2. Okay, so we have succeeded in finding A0, AN, as well as also BN. Okay, so now we have found our expressions, right? So ideally, how this would have how if you want to think about it, this therefore means that we now have our differential equation, which was given at the first page, which was mu plus cu dot plus ku dot. It's now it's now can be written as an expanded expression as mu plus cu dot plus ku. It's now going to be equal to, so let me just write the general expression, which is a0 over 2 plus the summation of n is equal to 1 to infinity of the following, right? So if I recopy again that that general expression, so of an cos n omega t plus bn sine n omega t. Okay, so what this is basically what we have done this far, right? Whereby we found what is a0, what is an, what is bn. So in order for us to now solve, to find the particular solution for this particular equation, this therefore means that, well, how about we use superposition? And what I mean by superposition is that I can safely say that, well, this expression is the same as saying plus ku, right? So how about we find the individual solution for this particular expression plus the solution to this particular expression, which is mu plus cu dot plus ku is equal to, now the first one, it's summation of an cos omega n t. Okay, then that's the second one. The third one, so it's going to be also plus the solution for mu double dot plus cu dot plus ku is equal to summation. Okay, is equal to summation of, in this particular case, bn sine n omega t. Okay, so in actual fact, I'm using the principle of superposition to separate the individual forcing function, since it's now a series, and find the individual solution that is associated with this. So from this one, I'm going to get a particular solution that is associated with this, which I'll call xp1. Then I'm also going to find a particular solution that is associated with this one, which I'll call particular solution 2. Then lastly, I'm going to have this solution that is associated with this term, which I'll call particular solution 3, right? So this therefore means that my overall particular solution is going to be a combination of xp1 plus xp2 plus xp3. Okay, so how do we go about to find what is particular 1, particular 2, particular 3, and particular 4? Well, we already, it's now, since it's now harmonic terminology, it's going to be now very easy. So on this slide, I've already shown you some of the general particular solutions that is associated with the term. So xp1, so this will be xp1. So if I can bring out my pen, so this will be xp1, this will be xp2, and this will be xp3. Okay, so we are just going to evaluate. So in this particular case, just take note, aj is the same as an, and bj is the same as bn. Okay, so j is just the same as n n which we had in the previous page. Okay, so we have already found what is an, what is bn, what is, we just don't have n, we also don't have phi, right? So what we can do is we can actually evaluate what is xp1, since we have already calculated what is a0, right? And we know what is the stiffness k, right? So for xp2, we found that an, you still recall an, I think an was 0. So an was 0, as can be shown, as can be seen here. So that means that we don't have an xp term. So this is, all of it is going to be 0. Okay. Then lastly, for the particular solution, which is xp3, right? What you are going to see is that we're going to need to find zeta. And remember, zeta is zeta. We can easily find zeta. And the way we can find zeta is we just use our knowledge, which is the ratio of the damping coefficient and the critical coefficient, which is just going to be C divided by the square root. So square root of 2K M, right? So we have zeta. Then our R is going to be the ratio of the excitation frequency and the natural frequency, okay? And lastly, what else do we need? So we also need to just, I think what's also important to note is the excitation frequency. So the excitation frequency is the period divided by 2 pi divided by the period. So this will be our omega that we're going to use then. Okay, so Bn, which is equivalent to Bj in this case, we have already determined it. K was given in the question. Phi, we can evaluate it, but in this case, since we are not given, remember n is referring to the number of terms. So we're just going to leave it as n. J, we are not going to evaluate it, which is equal to n in this case. So having done that, you are able to, if you evaluate your XP1 and your XP3, you will then be able to find what is the overall particular solution associated with this. Okay, so you see that what's left is just for you to evaluate those terms. If you find those terms, you are home and dry, and you find what is your particular solution. I hope this video helped, and if there's any questions, please feel free to leave a comment. Subscribe to the channel for more content, especially for more upcoming videos with regards to mechanical vibrations. So if you have any questions, feel free to drop them in the comment section, and I'll gladly be able to interact and also help out on the questions that you would have posted in the chat. But otherwise, see you, and have a lovely day. Cheers.